bases are the same, you're multiplying bases. What do you do with the powers? What do you do when they're dividing? What do you do when it's a base and a power and another power? So a lot of exponential rules that we've already worked with. How do you deal with negative exponents? What the power of 0 equal? Things like that. Growth and decay. Now, a lot of application in these problems. Again, specifically in the business, finance world of things. If any of you have bank accounts in some sort of a financial institution, they're calculating the interest that they gave you based off of either a compounding interest formula or a simple interest formula. And we're going to look at those and see how they work. So growth and decay. Growth obviously is over a period of time. My value is increasing. Decay, my value is decreasing. And we have examples of this. We know that you guys probably heard the whole car scenario. You go buy a car, you drive it off the lot. The next day, it's not going to be worth the same it was when you purchased it, right? So things depreciate over time, and things appreciate over time. And that's an example of a depreciation. You have, like in your biology or your chemistry classes, you guys are probably running labs where you're checking out, I don't know, some sort of a bacteria in a petri dish, and that petri dish, you stick it in your little oven to get that thing going, and you go back the next day, and bam, there's more bacteria. So you got exponential growth stuff with that. Decay. I dig in my yard and I find a bone, and hey, it's a bone of a mammoth. What do you know? And we want to know how old the mammoth is, and so you have those carbon dating scenarios, and that's another example of you got decay going on. So those are the types of problems we're going to work with. All right, the big deal on the growth and decay is we always have to base our rate of increase or our rate of decrease off of our original amount. So if you're talking dollars, I put money in the bank, and that money sits. Then a month later, if I have a compounding monthly type thing, I'm going to add on to that original money some percentage, and now I have more. And then I let that money sit again. And at the end of the second month, I have that original amount plus the little more that gathered interest, and that now is going to gather interest, and now my money starts to increase. So it's not linear, but it's exponential. The longer I keep it in there, the larger my amount grows. So that's the kind of thing that happens. So the thing is, this is going to be we got to remember this part of these problems, original amount, usually referring to 100% of whatever it is. Number of bacteria, number of dollars I've invested into a bank. I'm always basing everything off of 100%, 100 plus or 100 minus when we're doing this stuff. So, college tuition. Oh, this is a depressing subject. When I started school, Cal Poly, I paid $393 per quarter in tuition. When I left, I was paying over $1,350 per quarter tuition. So it like 400%, 300%. You guys are going to pay significantly more than that. And that's just tuition. That's not your books. Your books, like a book, like this is a college text right here. That's probably $95. The wider the book, and they're designed to fall apart after a year. And you sell them back, and you bought it for $95, and they say, hey, you know what? We're going to give you a deal. I'm going to give you $5 for that. And then they go around and they sell it for $40. It's a racket, I tell you. It's a racket. All right, so here we go. 15 years ago, college, 2000. Obviously we're just arbitrarily, we don't know what college this is. $2,000 a semester. This is just tuition. It's just paying for my units. This isn't paying for my books or anything. $2,000 a semester. Assuming those costs have increased at 10% a year, how much would this college cost us today? So we're always going to be developing an equation, and that equation will be exponential in form usually. It's usually a function. So here you see we have cost as a function of the time. So going back to what we were doing with chapter 4, that's a C of T problem. I want all my cost equations to be related somehow to time only. We got a couple other pieces of information in here that are going to be helpful to us. This original tuition per semester 15 years ago. That's going to be helpful for us. This would be helpful for us because it takes us back 15 years. We're talking now, what, 1998. And then this is going to be helpful for us. Anytime I have a percentage number, that is going to be my rate of either an increase or a decrease. And so for increasing, this means I'm going to be adding to it. But my rate, and I want to convert my rates when I set up my formulas. I want to change them to a decimal form. So just move the decimal to the left, right? That's how we change our percentages into a decimal, divide by 100. So those are all the things we're looking for in this problem. And it's sometimes helpful for us to develop a little table here so we can kind of see what our equation might look like. You guys are going to get to the point, though, where you're going to know, hey, here's my generic exponential function. I just need to find the right parts. I need to find the initial amount. I need to find what we refer to as my growth or decay factor. And then what's my time period. That's the stuff that we're going to be looking for. All right, so let's fill in the table. Time 0. Again, we're talking 15 years ago, right? Cost would have been $2,000. All right, at the end of 1 year, our costs have increased by 10%. So what am I going to do to that $2,000 to figure out what's my new tuition? What's that? Move the decimal once. What do you mean move the decimal once? Oh, okay, so you're saying my increase is $200. Yeah, so what did I multiply 2,000? 10% or 0.1, right? All right, so 10% is, move the decimal one to the left, so 10% of 2,000 is 200. That's what I'm going to now add on to, so here's the part we got to get squared away. I'm adding that onto my original amount every time. So I'm adding it onto 100% of what I started with. So I'm actually not going to be adding 0.1. I'm not going to be multiplying by 0.1 to the 2,000. I'm actually going to be multiplying by 1.1. Because if I just multiplied 2,000 by 0.1, that would say I've gone from a cost of $2,000 to 200. Woohoo! That would be sweet.
Would be awesome.
And that, if you find a college that's doing that, chances are it doesn't exist. Yeah, wow, that would be exciting. So we're doing this. We are using 10% of 200, but we're having to add that onto 100. So I'm doing this. I'm going to be multiplying by 100% of something, $2,000, and I'm going to add on to that the 10% more. So it's like doing this. I'm multiplying by 1.1 to get to the next guy. 2,000 plus the 10% of 2,000 makes this become 2,200. So multiplied by 1.1. All right, and we're going to do this each time. We're going to figure out what did I do to get to the next one. So now, after year 1, it's now $2,200. Year 3 is rapidly advancing, and we now get another 10% increase. So, money-wise, what's my increase? How much am I going to add now? $220. But I'm adding that to what? I'm adding that now to the 2,200, which is the new, quote, original amount, right? But if we always go back and refer to this guy as my initial, this is called my initial amount. We're always going to go back and refer to that. I would say, all right, I'm going to take this and I'm going to have to multiply that one also by 1.1%. 100% of the original, 2,200, times another 10%. And I'm going to get 2,420. And then I'm going to do that again. I'm going to take 2,420, and I'm going to have to multiply that by the 100% that I have, plus the 10% more. So what am I doing each time is I'm multiplying by 1.1. The original amount from that year, plus the 10% to get to the next. So this is going to be, what, another 242 bucks? So 26.62 would be my new increase. And again, that's not a linear pattern. If it was a linear pattern, I'd see the same dollar amount per year. But I'm not seeing that. I'm seeing that dollar amount slightly increase each time. So graphically speaking, we get this curve, this sweeping curve that's showing me an exponential thing. All right, but here's the more important part of it. We haven't developed our equation yet. Look at what happens from one year to the next. So here I multiplied by 1.1 to get to this one. And then I did it again, but then I had to multiply it by another 1.1, or 1.1 squared to get to the next one. And then here I did it again, 1.1, but this time it's the third time I had to multiply it by 1.1 to get to the next one. So you can see what happens is I have this original amount that we refer to, and I am raising to the power this 1.1 as my growth factor. So here's your generic exponential function. And this is what we started with in algebra 2, something like this. In identifying all of the parts, we've got y is known as our final amount. We have a, which is your initial amount. Probably have this on the next slide. Hang on. Yeah, I got it. B is known as your growth or decay factor. And then X is your time period, meaning it doesn't have to just be per year. That could be looking at something where it happens on a daily or over a decade or something like that. So time period doesn't have to be a 1 year, 1 day thing. That's our general formula, y equals ABX. So if we set that up here with our cost as a function of time, cost as a function of time, I want to just see a t in here, and we follow this format, a, b to the x power. All right, we've got to find out what a represents in this problem. We've got to find out what b represents problem. We've got to represent x with something. A is our initial amount. Well, we knew that our initial amount in this problem was be at a $2,000 college tuition for semester cost. Then we increased this cost, and we increased it by an amount of 100%. Because I'm increasing, I'm adding to it whatever my rate was. So you're going to oftentimes see B written as something like this, 1 plus or minus a rate value. 1 representing 100%, R would be the decimal equivalent of that percentage. So we have a 1.1 because we have 1 plus 0.1 giving me 110%. So that's what's going to go right here for our B. And now this x, actually, we're using the variable t because we're referring to time, would be our number of years. And this is happening, this change, this increase is happening every year. If that changed, if the wording was different, let's say the wording said, you're going to increase your college cost every other year. Now our t, which would represent our time period, would be a 2-year cycle instead of a 1-year cycle. So the t can be the tricky part of the problem, knowing what is my time period that I'm referring to. It doesn't have to be a per year. And there we go. There's our equation. Cost as a function of time, the only variable in there is t. And then now I'm able to, with the equation, project out. Let's assume that those costs increase 10% for 20 years. How much am I going to pay to go to that college? And that's, again, the modeling aspect of mathematics. It doesn't necessarily have to be that it's going to be a 10% thing. In fact, the trend over the years has been not that. The trend over the years has been, it's kind of ratcheted up on a yearly basis. 10% to 11%, 13%, 14%. So same thing with like medical costs for insurance. You don't know if your mom and dad talk about insurance premiums and stuff. Same thing happens there. All right. What questions do you have there for that problem? Yes, ma'am.
For the T, is it like 15 or 17?
Great question. So if I wanted to know 15 years, yeah. From where this started, I would plug a 15 in there, and that would give me my cost after 15 years, exactly. Now, here's a question. Can I use these things to go back in time? Can I project back in time with something like this? Yeah, I can. Again, we're making an assumption that this 10% trend is happening and has happened. So if I wanted to, I can go back in time. And I want to say, all right, what would the cost have been 20 years ago? Then I put a negative 20 here for my T. And then I just project it backwards. So yeah, you can use them to go and take a look at something that may have happened in the past. But you're making the assumption that that rate of increase has happened for however long you're going back in the past. Any other questions? That's a good question. Any other questions on the CFT thing? All right. So there it is, written a little differently. There's our B. We talked about the B. There it is right there. This little subscript O thing always means initial. For you guys that are in physics, you probably already know that. B sub O, initial velocity of something. Well, this is A sub O, the initial amount of something. That's the same equation, y equal a dx. It just looks different. I just changed some variables. This is one that's going to help us when we get to, well, this is like what our typical finance-related questions would be. But they don't have to just be finance. It could be something else as well. I could go back to the biology example of growing bacteria. You could use an equation like that. And then these are the graphs of our exponentials and the parent functions for them. They change a little bit depending on the base value. So these two particular ones that are shown are for a base of 2. Had I changed that base to something other than 2, a 5 or a 10, all it makes a difference with the change of base is the graph. The bigger the base, the closer the graph vertically stays next to the y-axis. And I'll show you what I mean by that in just a second. Are we good on these amounts? These are what we had before. Is everyone good there? Okay, so what if we had a y equal 10 to the x? How would that look different than this y equal 2 to the x? Well, it's going to look very much the same thing. It's just going to stretch a little bit differently vertically. So it's going to still go through that point. And how do we know it goes through that point? Well, put a 0 in here for x. And do we remember that a 0 power means 1? Okay, so 10 to the 0 is 1. If I put a 0 for x, I get a value of y equal 1. And then if I went right 1, or plugged a 10 or an x equal 1 into that equation, 10 to the first power is 10. So instead of me going right 1, 2, which is what 2 to the x is doing, I would go right 1 up 10. So now the graph just stays, kind of still has this asymptote look, but then it's just going to stay closer to the vertical axis and then start to fan out as it moves up. So that's the only difference. Yeah.
So, no matter what graphing approach to formula, it will always, whenever it's x is 0, y will always be 1 no matter what. Correct.
Okay, question was, for a growth or decay function, if the x is 0, will the y always be 1? No. If I move this graph somewhere else, that will not happen. So if I translate it, so like this would take, if I did equal y equal to x, and I simply did this to it, now what that graph has done is it's moved right 1 and up 2. So it no longer goes through 0, 1.
So, but anytime you have a graph,
Right. Anytime there's no translation, you just have a parent, you're always going to go to 0. Every time. By the way, parent functions, there is a YouTube video that I did for parent functions. If you want to go check out the 9 parent functions, these are one of them. Exponentials are part of our parent functions. There's also exponentials, logarithmics, cubics, cube roots, squares, parabolas, reciprocal functions, and I think a linear. But anyway, getting the idea of the sketches for these things. If you want to look at parent functions, then go check that out. So a growth graph, as x gets big, so does y. And the decay graph, as x gets big, y gets smaller. That makes sense, right? The longer I have something and it's decaying, and I'm going to have less of that. Oh, wait. I have one more thing. Oh, there we go. Let's do one of these. The value of a house increases annually. What do you guys think? In today's market, is that true? Right of that. So, yeah, we start to see a trend. You guys follow kind of what's going on with the housing market, especially in the Sacramento area. There has been an uptick in housing prices. And so what used to be strictly a buyer's market, which means you kind of come in and sweep up, collect houses, is now going to become maybe more of a seller's market because you're able to get more money for your house because people are going to be competing on bids for it. So this is probably becoming a little bit more true than it was, say, 5 years ago. House increases are definitely on the way up. All right, so we got find the value of a $100,000 house for 4 years, and how many years will that be doubled? Good idea. Always start out with the generic formula that we're going to be working with, which is our y equal a sub 0, 1 plus 4 minus part of the t problem. And then we just got to find the right parts to fit. So there it is. There's our generic. And I want to fill in 2 things to be able to write the equation. And then the second part, part B, where it says, and how many years will it be doubled, then we're going to be having to fill something else to answer that question. But at least for part A, we can fill in our A sub 0 and our R value in here. And then plug in, in this case, 4 for our T to come up with this value now. All right, who's got a number for me? How much is the house worth after 4 years?
$181,063.
Is that what you got? $181,063.
$93.
Oh, and 90. We can't forget the 90. We don't want to rip them off. Yep. So, okay, how do we get that number?
93.6.
12.6 cents. Okay, what part of my equation is this? That's my R, but I'm going to change it to a decimal. What part of my equation is this? That's my A sub O. And then here, now how do I know that 4 does not represent a time period? There's a big word here, not a big word. There is a word telling me I know what my time period is. Annually, very good. So this right here tells me that my time period is 1 year. Meaning it's changing its amount after a year. So I have everything I need to be able to fill this thing in. We have $100,000. We're going to add to it because it says increase. We're going to add to it 0.16%, or not percent, 0.16, and we're going to run this out for 4 years. And then we get our number, which was, what was it again, $181,094 cents? Okay, now we're talking pennies. We're probably not going to be too concerned about that. Probably what industry would do with something like this is they'd say, oh, that house is worth $181,000. They might even round it up. But for you guys, you're going to give me the exact value for these things. So there's my, now what this is A of 4. That's after 4 years how much the house is. All right, who's got a B answer? Anyone have a B one? That was a little different. A couple different ways we could get a B. Yeah. What'd you get?
About 5 years.
About 5 years. What did you get, Carmen? 4.6. So you got an exact. Did you get an exact too, but you just rounded?
No.
Okay, how did you guys get your numbers?
Log.
You did log. Great, good. So hopefully you remember from Algebra 2, what does a logarithm do? A logarithm helps me solve for a variable that's a power. There's another way I could do this problem. Anyone else know how we can do it? Yeah?
Did you put in $200,000 for Y and solve for?
That's what we are actually. That's what we're going to have to do. But so besides using a logarithm to do that, there is another way we could find that answer. Actually, there's two others. Not as fast as doing a logarithm. Trial and error. We can trial and error. We can start putting in values of t until we get to 200. Or we could graph it, and then we can figure out where is this 200 mark. So we can do that as well. All right, but probably fastest way is to deal with the equation. Now here's the trick on this one. The value is doubled. That tells me what my y is. That's my final amount. So you're going to have to, oftentimes there will be problems that state in a phrase like this what your actual y value is or your a value. And you got to understand what we're referring to. So that's my y that I end up with. So in this equation, I'm going to have 200,000, the value of the house. Started at 100. We're still going at 16%. By the way, I'd rather you write it like this than 1 plus 0.06. Just simplify. And then now we're looking for that. We're looking for how long does it take us to do that. So we solve for t, divide by 100,000, we get 2 is equal to 1.16 to the t, and here's where I can start trial and error, start plugging in some numbers for t until I get close to 2. We could now use a logarithm, and a logarithm would say this: log base 1.16 of 2 is equal to t. But some of our calculators, probably the majority of them, do not do that because we don't have log base everything. Most of these are log base 10s. And so then you're going to have to go and do your change base formula. Do we remember this? Just vaguely sound familiar. This allows me to find a base 10 value that I can then use my calculator for. How it works is this. In a log form, log base 1.16 of 2, the basement is in the bottom, and log base 2 is on the top. So you change base formula with this like so. T would actually equal log of 2 over log of 1.16. Base stays in the basement, 2 stays in the first floor if you think about it like a house, and you have this. Now I punch that in the calculator, but being careful how I do it. Log button 2 close with a parenthesis. Hit the divide button. Log 1.16, and that's going to give me my answer. What was it, Carmen? 4.91?
4.67.
4.67. So that's how we're going to get our exact value. So here's a question for you. What if I ask the question like this? When will the house be worth $200,000? What's your answer going to be? What year? We don't have a start year, right? But let's say we said 2000. It was 2000. It was $100,000. So if I ask the question, when will the house be worth 200,000? What are you going to tell me? So we have 2005 as an answer. What else could we say? 2004. Okay, let's figure out which one of those is right. All right. This says it's not until 4.67 years that it'll be worth $200,000. So in 4 years, which would be 2004, is it worth $200,000? No, it won't be worth $200,000 until the 5th year. So you have to say 2005. Yeah? A little weird to think about that way, no? Yes, sir?
So in the answer we say 5.
No. So in this particular problem, the answer is 4.67, or you could even say about 5 years. If I had a question that said, when will it be worth? I want a specific date. And that's when you would say 2000. If we said we're starting at 2000. Yes?
So this question on a test, which require exact value?
Yep. Yep. We're going to look for the exact value because we know how to solve the logarithm.
Okay. So your target is 5 without.
Right.
Satisfactory.
Yeah. I want an exact value in this. So we talked about 2 other ways to do it. One of them was graphing. Real quick on the graphing part of this. What am I doing? Where did it go? If I graph this thing on a graphing calculator, I'm going to get something that looks like this. It's going to do something like that. And I can use the trace button on my calculator and get the little blinking box to move along the curve. And I want to go find out when does it hit 200K. And then I can use the calculator to come up with an answer. I could also do the calculate option in the calculator and do that as well. So if you have a graphic calculator, you can check your answer there. But I'm actually going to be happy that you're using a logarithm because that's an exact. All right, what questions do you have on A or B? Yes, ma'am?
If you have a calculator that does do it automatically, do you have to show that last slide?
Good question. So if your calculator does the change-based formula, lucky you, you have that. I want you to still show the change-based formula. And we're going to come back to that in a couple of sections anyway. So if you don't remember, we'll have a chance to look at it. All right, so here we go. Lots of exponents. This is our review stuff. How many of you guys do have the calculator that does the change base? Yeah? A few of you do? Nice. Nice. You'd know if you did because you should have like a log ABX button. Something like that. Or log BX or something like that. All right, let's quickly go through these because we've seen these before. Nicely done, Ivy. Hey, listen, you're right next to me, just go like this. That'll work.
Yeah.
Don't be a distraction or Ivy's going to kick you out of the classroom. You have my permission. All right. Do you guys remember these rules here? Multiplying, add them, division, subtract them. Pause. The only one maybe to think about negative exponents. If you've got a base that's actually a fraction. So if we had, say we had a 2/3 to the negative first power, where you've got a fractional base. Remember that you had, and you're working with a negative exponent. It's simply a reciprocal to write it as a positive exponent. So I would simply flip this, and now it's a positive exponent. So those are the only ones you got to be careful with. That are negative. All right, so we got all our rules. Let's go use them. Simplify. Do I care about this 10,000 or 1,000 to the negative first power thing? Do I need to even worry about that? No, because I got that 0 hanging outside. It says whatever it is, whatever that stuff on the inside is, if I'm raising it to a 0 power, this answer is just going to be 1. Again, pointing out mistakes. Let's just take the 16 to the negative first, for example. Remember that a negative power means my answer is going to be, if I start with an integer number as a base, my answer should be decimal or fractional when I'm done. But sometimes what people keep doing in here is they write this as, like, what do you think some kind of answer is going to show up here for this one might be what? What do you think people are going to plug? Well, so that's what I hope that they will write. That is the answer. It's 1 over 16. Now some folks are going to write what? Negative 16. Okay. A negative out there is not something that comes out front as a coefficient. That's a power. And it says, first we want to make this positive, so we have to move that negative exponent somewhere else, which means if it starts as a numerator, you move it as a denominator to make it positive, and vice versa. So that's what we should end up, not negative 16. So in this one, leave the 2 and 8. It's already positive. Leave it where it's at. But these next two, this is where I can kind of simplify my life a little bit. So how many of you are, I like to move negative exponents to become positive first before I work with them? There's like, sometimes there's two groups. There's the group that does that, and the group that says, I don't care, that's going to work with them. You guys movers? You're a mover. All right. So if you're a mover, you're going to take this 4 to the negative 5th, and you're going to put it down. And you're going to take this negative first of the 16, and you're going to move it up. And so it's going to look like this. And then maybe you come up with your answer from here. So this is a type of a problem that we can do without a calculator. In fact, there will be parts of our quiz and our fun times that we do no calculator. This would be one of them. How can I simplify that process right there? There you go, good. So Drache recognized that 16, 4 are both base 2 numbers. So if we change all of those to base 2 numbers, then I can do my property exponents. Same bases, multiplying and add powers. So this becomes 2 to the 8 times 2 to the 4th, which is what 16 is, and then that's still being raised to the first power. And all of it over 2 squared, which is 4, and then it is being raised to the 5th power. Now I have the same bases. Now I'm going to apply my properties of exponents. 2 to the 8, 2 to the 4th, all over 2 to the 10th. There's a power of powers going on there with that 2 and 5th power and the 4 and the 1 in the numerator. Did I have add the powers for the top? So the 8 and 4 gives me the 12, 2 to the 12, 2 to the 10 equals 2 squared, which is 4. Because I'm going to subtract the 10 from the 12. So we're going to want to write all our answers with positive exponents, and we'll simplify things down. Are you good? You guys have questions on this? All right. What about here? C and D. What should we do with those? Yeah.
Separate each factor into under its own radicals.
Okay. Yeah, yeah, you could do that. You could separate because it's all under a radical right now. You could separate it into this. But I'm gonna suggest something here. I'm gonna suggest that you kind of think of a radical of a quotient as like it's a grouping symbol. And we want to think about parentheses, exponents, multiplication, division, right? So if I think about trying to simplify what I can underneath the radical before I separate it, that's oftentimes going to be an easier way to do this than versus separate it and then stick it all back together. So if we do that, if we try and work within the grouping symbol of the radical, this becomes, again, 25, 5, and 5, 125 are all base 5 numbers. So we're going to change them all to base 5, and this becomes 5 squared times 5 at the end, 5 cubed to the 2 minus n power, and this is still underneath this radical. Yeah?
Shouldn't it be 5 squared to the third?
Oh, yeah, 5 squared to the third. Thank you. So I have, going this way now, I got 5 to the 6th. Times 5 to the nth over 5 to the 6 minus 3n. So I'm going to distribute that 3 power. And again, still underneath the radical. I've got a power property on the top where I add them. 6 plus n. 6 minus 3n, still underneath. Then I've got quotient properties, subtract them. 6 plus n minus, and I'm going to stick this in parentheses because it's a distribution problem now. Minus the power of 6 minus 3n, and still underneath the radical. Then what do we get? 5 to the 4n power. The 6's are going to cancel. 5 to the 4n power underneath the root. And then, because this thing started as a radical, we're actually going to leave our radical simplified. I could change it to an exponential because 1/2 power is the same thing as a square root. So this could be the same thing as 5 to the 4n to the 1/2 power, and now it's 5 to the 2n. There we go. Where's my 5? And then our last two. Okay, what's tempting to do on that part B problem? Yeah, you want to think about distributing. Why can't you? What's the thing that's preventing us from doing that? That plus sign in there. That's a binomial raised to a power. It's the same thing as thinking about x plus y squared. I don't just x squared and y squared. I have x plus 2xy plus x squared plus 2xy plus y squared. Well, I can't kind of do that with this one. I can't just distribute the -1 and make that become a 2 and make it become a 2. I have to, first of all, well, what I would do is I would just take the -1 power and I'd write this as a positive exponent. Which means I put all that stuff down below. When you do that, however, the -2 powers that are in that parenthesis are going to stay negative. Because the only thing I'm changing by moving the a -2 plus b -2 down below is I'm changing this negative exponent to a positive. That's it. So by doing this, I just change that to a positive one, not a negative. complex fraction. How do we get a complex fraction out of that? 1 over a squared plus 1 over b squared. Since it was to the first power, we're okay with doing that. And then now I gotta simplify that. So I have a couple different things I could do. I could say, let's find the common denominator of all the parts and multiply everything by that common denominator. I could just work with the top or the bottom. The bottom in this case just has 2. So we're going to go with, let's just make everything multiplied by a squared b squared. And then this would become b squared plus a squared. That's the simplifiers we're going to get for that. Cannot cancel the b squared at the top and the bottom because b squared plus a squared is not in factor form. It's not a negative. If that was a negative, that was a b squared minus an a squared, then I could write it out as b plus a, b minus a. But even if I did that, I'm still not able to cancel anything up in the numerator. So that's as simplified as we get for that. Same kind of thing's going to happen here with e. So I'll let you guys kind of tackle e. You're going to end up with some complex fraction work there. You got some negative exponent parts that you got to make positive. And then you think of numerators and denominators. You have negative exponents in the numerators. It's not as simple on this one. Again, this plus sign is the thing that's preventing you from doing it. You can't just take x to the negative third and move it down. And take the x to the, although you could do it with the x to the negative 2. But you can't take the x to the negative third and move it down because it's not a factor right now. It's married to that x to the 5th factor. So I'll let you guys work on that. We'll check in here in a minute and see what you got. Here, we'll record. Done. Anything else? We're good? Yeah.
Why? I mean, you have x to the 5th plus 1 over x cubed over x to the negative 2.
Yeah.
How did you get the next step?
I took this x to the negative 2 power and I put it into that numerator. So I just shifted it up here to make it positive.
Oh, okay. Yeah.
And that's where that step came from.